Practicum number 5 in computer organization and architecture. The first program analyzes how the number of pipeline affect the performance of the processor. First, the program defines the number of instructions executed by the processor and the range of the pipeline values. Then it calculates the execution time for two cases, that is for non-pipelined execution and pipelined execution. So in non-pipelined execution, each instruction must complete all stage before the next instruction. So the total execution time is the number of instructions multiplied by the number of stage, which is given like non-pipeline of I is equal to n cross ki. So in ideal pipelining, instructions overlap during execution. So after the first instruction executes, a new instruction completes every cycle. The program uses this concept to compute the ideal pipeline execution. That is, pipeline of I is equal to k of I plus n minus 1. So next the program calculates speedup, which is the ratio between non-pipelined execution and pipelined execution. This tells us how much faster pipelining makes the processor. Finally, the program generates a graph showing the relationship between the pipeline stages and speedup. The graph helps demonstrate the increase in pipelining stage generally improves performance, but the improvement eventually becomes slower. So this is the graph between effect of pipelining stage versus pipelining stage. The second program demonstrates how pipelining hazards affect the processor performance. In an ideal pipeline, instructions flow continuously through the pipeline. However, in real processor, hazards such as data, structural, and control can interrupt the pipeline. These hazards cause the processor to install stall cycles, also called pipeline bubbles, which temporarily stop the instruction execution. The program first defines the number of instructions and the pipeline stages, then introduces a different number of stall cycles. It calculates the ideal execution, assuming there is no hazard. After that, it calculates the actual execution time and the pipeline stage, then introduces a different number of stall cycles. It calculates the ideal execution time, assuming there is no hazard. Finally, the program plots a graph showing execution time versus stall cycle. So this is the graph which shows the effect of hazard on pipeline performance versus execution time and the number of stall cycles. So the third program analyzes the difference between instruction throughput and instruction latency in pipeline processor. First, the program calculates the execution time for both non-pipelined and pipelined process using a fixed number of instructions and pipeline. Here, instruction is given as 40 and the number of pipeline is given as 5. Then it calculates the throughput, which represent how many instructions are completed per clock cycle. In pipelining, multiple instructions are processed simultaneously, so the throughput is higher compared to non-pipelined execution. The program also calculates the instruction latency, which is the time required for a single instruction to pass through all pipeline stages. Even in pipelined processor, the latency remains the same because each instruction must still go through each stages. Finally, the program displays a result and generates a bar chart comparing the throughput for pipeline and non-pipeline processor. So this is the comparison of throughput between non-pipeline and pipeline. It shows throughput is very high for the pipeline processor. Thank you.